Day one, we're going to be looking at proofs again. And I know we did proofs last year in Integrated 1 when we did triangle congruence, and we did them again this year. I believe it was chapter 2 when we did triangle similarity. It might have been chapter 3. I don't remember exactly. So we're going to do it again, but this time we're going to be doing them with forward like quadrilaterals and really making proofs about quadrilaterals, and we'll talk about that a little bit more as we go through this. But I just wanted to introduce with the story I always introduce with. So here's the story of what I did last night. This is fictional. This is not actually what I did last night, but nobody cares. So I took a nap and changed clothes. Oh, but I went to a soccer game first. I burned the bread. My wife and I walked our dogs, Gordon and Harper. My wife did not like it. I went to bed. Oh, I also cooked dinner for my wife and I. We watched a movie together. So hopefully you realize the story doesn't make a lot of sense. And the reason is because it's out of order. And when we tell a story, we want it to be in order so that it makes sense. And it's the same thing with a proof. It's really important that a proof goes in order, like a logical order that makes sense from one fact to the next. And that's kind of what we're going to be looking at here. So the real story was I went to a soccer game. Then my wife and I walked our dogs, Gordon and Harper. I took a nap and changed clothes. Then I cooked dinner for my wife and I. I burned the bread and my wife did not like it. We watched a movie together. Then I went to bed. And hopefully that makes a lot more sense. So we're going to be doing something called two-column proofs and instead of flowcharts. Depending on which teacher you had last year, you might have done like the flowchart thing where you sort of have a fact in the middle of the bubble and then the evidence outside it. Now what we're going to do is have a fact in one column and evidence in the other. And again, depending on your teacher, you may have already dealt with two-column proofs a little bit. You may not have. It doesn't matter. There's really not a big difference either way. So we'll just sort of jump into it, and hopefully you can see the similarities between a flowchart and a two-column proof. So first of all, what's given is 5x minus 4 equals 6. And we always want to start with what's given. So we're going to start with 5x minus 4 equals 6. And we know that's true because it's given. So again, here's a fact. It's a fact that 5x minus 4 equals 6. And we know that's a fact because that was given. Now, at this point, hopefully we all agree that I would add 4 to both sides. And I would end up getting 5x equals 10. And the thing that allows me to do that, it's known as the addition property of equality. And that's just a fancy way of saying I added 6 plus 4 equals 10. So honestly, I know usually I have kids start to stress like the addition property of equality. In a proper geometry course, we probably would spend a little bit more time on this, but for now I'll just take addition or even math. I don't really care. It's not the point. The point is that we hopefully can agree that that's true. So now I'll divide both sides by 5 and I will get x equals 2. And again, we know that's true, and hopefully you guys can sort of guess what this is, but it's the division property of equality. So this is a proof that we have done here now. So we've started with a given, that's what we started with, and we ended with what we were trying to prove. And that's really the process that we're going to use over the next week or two while we're doing these proofs. Is there's some tricks to proofs, a plan. I would say a plan to go through these things, and one of them is start with what is given and end with what you're trying to prove. I just think that sort of helps fill in what's missing. So let me go ahead and set up another one real quickly, and then hopefully we'll sort of see where we're at. The next one we have is 2 times 2x plus 5 equals 8, and we want to prove that x equals negative 1/2. So I would love it if you would pause this video and try this for yourself to see if you can feel for this, at least to start with what you want to begin with, and if you can end with what you want to end with. And so we know that we want to start with 2 times 2x plus 5 equals 8. We know that because it's given. And we know that somewhere down here, maybe we don't know what number it's going to end, but we know that we're going to end with x equals negative 1/2, right? And maybe we don't even know why that is yet. And again, we don't know the number of this yet, but we know that's what we're working towards, so we can sort of fill some of this stuff out. So the first thing I would do here, and there's a bunch of different ways I could solve this equation, but the way I'm doing it here is I'm going to say 4x plus 10 equals 8. And the thing that allows me to do that is known as the distributive property. and again, it's just sort of using math that we know to be true and just saying how we know we can do it. So it's a fact that if I subtract 4 from each side, I'm sorry, 10 from each side, I'll get 4x equals negative 2. And again, what allows me to do that? It's the subtraction property of equality. From here, I'll divide both sides by 4. And I will get x equals negative 2/4. Again, we want to be real careful. We're not going to jump down to the end yet. So what we have there is the division property of equality. And then at this point, I think I can say x equals 2/4. Well, I can say that x equals negative 1/2. And I would say that that's just simplifying, right? I just simplified those fractions. So again, you can see I've gone through step by step on how to solve these things, and for each step I've said why I'm allowed to do that. That's the fact and the evidence that allowed me to prove that x equals negative 1/2 for this given equation. Talk about when I'm going over these quadrilateral proofs is like, why do we study triangles so much? Like, what was the big deal with triangles? When I was a kid, I was like, man, I know a lot about triangles, but I don't really know why I know them. And hopefully this makes sense, that when we have other shapes, they're made up of triangles, right? So this is a quadrilateral. If I have a pentagon, again, it's also made up of triangles, or I could even take a pentagon and break it up this way into triangles, right? So what they realize is, you know, if you know about triangles, you know a lot about other shapes, to the point where I always get a kid at this point who says, yeah, well, what about circles? Triangles don't make up circles. And you can actually see that when we're looking at, it's called the unit circle. You'll learn this next year in Integrated 3, but you can see triangles actually do have something to do with circles as well, which is kind of interesting. They make these wave function, which is pretty cool. You guys are going to learn some pretty cool math next year if you decide to take it. But anyway, so that's why we study triangles so much, is because they do make up other shapes. So if we learn about a triangle, then we can apply that knowledge to these other shapes. Again, so if it's ever seemed weird that we focus so much on triangles, that is why. And let me go ahead and set up the rest of this video. There's a couple of note pages for this chapter that I made, and I think that they're helpful. Obviously, that's why I made them, although, you know, maybe they're not helpful, I don't know. But there's a couple of things I like to remember when I'm doing a proof that I think are really, really, really worth remembering. One is, it's always a good idea to start with the given and end with what you're trying to prove. You can fill in the top of the proof down and the bottom of the proof up, so that way you really only need to fill in the middle. And I think that that really sort of helps. Another thing is that given may become evidence later in the proof. Like, it would be weird if I told you, like, hey, my shoe size is size 9, right? Like, who cares? It has no relevance at all. So, like, the fact that they're telling you something in these problems is because you're going to use it later. Like, they wouldn't tell you that something is parallel to something unless they expected you to use that knowledge later. So again, just be aware that anytime they give you something for a problem, you should expect that to probably become evidence later in your proof. And that's why they're telling you that. So it's just worth considering that. And these 5 things that I'm saying, I'll try and point them out as I go through the chapter as to the importance of them. So know your shapes and the definitions of those shapes. That's going to be a big one. And that's kind of like this given one, right? If they give you that something's a rectangle, well, what does it mean if something's a rectangle? Does that mean that there's 490 degrees angles? Or does that mean that the opposite sides are equal? Or does that mean the opposite sides are parallel? Or does that mean all of it? Like, what does it really mean to be a rectangle? I think most of us probably don't know that. And we'll talk about this more in a minute, but it's good to know the exact definition of these shapes and have them handy as we go through here. Or if it says, prove that this is a rectangle, what does that mean? Again, do I need to prove the opposite sides are equal? Do I need to prove the opposite sides are parallel? Do I need to prove all the angles are 90-degree angles, or do I need to prove all three of those things? So that's what I mean by know your shapes and definitions of those shapes. If they tell you lines are parallel, you should be looking for angles. And if they tell you that, if they give you angles, you should be looking for parallel lines. And the reason why I say this is because whenever kids see parallel lines, they immediately think the sides are congruent. Parallel lines, you're looking at those angle relationships that go all the way back to junior high, and we covered in chapter 1 alternating interior angles, corresponding angles, vertical angles. Those are the kinds of angles that we're going to be looking for if we see parallel lines. And then this last one's a huge one, triangle congruence, right? It used to be an integrated one. We were just trying to prove triangles congruent. But there's something that's known as CPCTC. So corresponding parts of congruent triangles are congruent. They work together. And real quickly, what that means is if we know that we have two triangles that are congruent, like if you tell me, hey, look, these two triangles are congruent, whether they are or not is irrelevant, right? But if we say, hey, these are congruent triangles, and then you tell me, look, this is 5, 7, and 10, and 5, 7, and 10, I say, oh yeah, look, these are congruent triangles because of side, side, side congruence. I hope we can all agree to that. Well, then what if you tell me that this angle right here is, 70 degrees? Well, what angle does this have to be? I know it equals 70 degrees. And how do I know that? Well, because I've already proven that these triangles are congruent, right? So CPCTC, corresponding parts. This is the angle across from 10. This is the angle across from 10. They correspond. Congruent triangles. I just proved that these triangles are congruent. They're the same size and same shape. Well, those corresponding parts are also congruent. So once you prove triangle congruence, you probably proved them for a reason, because you're going to grab a different part that you didn't prove and say they're congruent as well. And again, I know this might be a lot thrown at you real quickly, and it's not what I'm trying to do is sort of overburden you with this stuff, but I do want you to see sort of that these 5 things are going to keep coming up, and I will keep referring to the sheet. And so hopefully by the end of the chapter you will feel comfortable with these 5 different things, and these are just tricks that we're going to use to help us fill in these proofs. So if you tell me these triangles are congruent, I'm immediately going to assume I need to use CPCTC. If you tell me I'm using CPCTC, I know that I need to prove triangles are congruent right in front of it, right? So the other notes for this chapter, again, the shape definitions. What does it mean to be a quadrilateral? What does it mean to be a kite? What does it mean to be a trapezoid, whether it be isosceles or right, a parallelogram, a rhombus, a rectangle, a square? So we're going to want to know exactly what these definitions are. Also, we need to have these, we have fact and evidence, right? So this is almost like an evidence list, really. It's a list of our evidence. So these are different evidence we might use. We might use given, we might use alternate interior angles, we might use corresponding angles. Like, hey, how do you know those angles are congruent? Oh, because they're alternate interior angles. Or how do you know those sides are congruent? Because they're reflexive sides. Vertical angles, midpoint, right? Oh, these side lengths are the same. How do you know? Because they're the midpoint, and that's the definition of a midpoint. We have angle bisectors and side bisectors. So we'll be using both of these sets of notes. So I would strongly encourage you to fill these notes in as you go, and to really make sure you understand both pages of notes, because if you don't, that is going to be a problem as we jump into this chapter. I did want to point out, I really like this page. It's called Prove It, 2-column proofs practice tool. You can see it's ferromax.com. Anyway, there's a bunch of different proofs. Some are easier, some are more difficult, and I want to show you how this page works and end with this proof right here, complementary angles 2. You can see it's an easy proof, and you can just sort of see how this page works. So first of all, it's going to make you choose one of the statements, and then once you choose the statement, then you're going to go with the reason why. So first of all, here's the given. Angle 1 and angle 2 are complementary. So I feel like this might be a good choice. Angle 1 and angle 2 are complementary. And how do I know that's true? Because it's given, right? And you can see now it jumps to the list of reasons. So I'll take given. Now I'm down to 2 choices. So I'll say, hey, angle 2 and angle 3 are complementary. And again, how do I know that? Well, because it's given. And then finally, my last one is, I guess I'm going to end with the proof, right? Angle 1 is congruent to angle 3. Well, how do I know that? Well, because if two angles are complementary to the same angle, then the angles are equal in measure. So, and now what I can do is I can check this and see if it's right, and you can see it's success. It was obviously a very easy proof. I just wanted to, again, show you how this web page works and draw your attention to it, because I think it's good practice. Also, hey, look, we started with what was given, and we ended with what we were trying to prove. So I think that's just an example of that. So that's it for day one. Kind of a nice soft start to this chapter.